Page 359. It's an electric potential question. We're just going to treat it like it's an electric field question or a Coulomb's law question. So basically, in fact, we don't even really need the question. Let's do it like this. So here's a charge A is negative, charge B is positive, charge C out here is positive. And let's say that they're in an equilateral triangle. Okay, so that means that you automatically know all the angles. So a straight Coulomb's law question might be, what is the net force acting on B? In order to determine that, all you have to do is draw the free body diagram for B. So here's B. All right, so A is negative. Now, we know the physics, right? We know negative attracts positive, positives repel, negatives repel. So we're not going to put negative signs in for the Q's when we use Coulomb's law. Instead, we're going to keep those all positive, and we're going to set our directions based on our knowledge of the physics. So the free body diagram tells us the direction of our vectors. So B will be attracted by A, so we're going to have the force of A onto B in this direction. But C is going to repel B, so C is going to be acting in this direction. So here's the force of A onto B, and here's the force of C onto B. This angle theta is easily found. If it's equilateral, then that would be 30 degrees, obviously. So we can call up and write positive. Doesn't really matter what directions we choose, as usual. And we're going to find that net force. So the x component of the net force would be the x component of FCB minus FAB, which would be FCB sine theta minus FAB. And the y component would be, well, just there's no component here, just the y component of this, which would be minus FCB cos theta. All right, so once we find these two components, then we would just use Pythagorean theorem to find the net force. So it's going to look, so it looks like we're going to have probably a net force, something like that. So we'll just say that when we add these two together, it winds up looking like this. That's right angle. That's some angle theta. We'll call it alpha. That's some angle that we have to find to state our final answer. So Pythagorean theorem and inverse tangent, or in trig in some way, gives us the final answer. But first we've got to find FCB and FAB. This is where Coulomb's law comes in. So FCB will be K QC QB over RCB squared. FAB will be K QA QB over RAB squared. Obviously, you would need to know the separation between each of the charges in order to solve that. So these would all be known values. You'd plug your FCB, FAB in here. You'd solve for your components, put it into a triangle, use Pythagorean theorem for your net force, use inverse tangent for your alpha. State your final answer. So it's the same thing we've been doing like forever. This would be a boilerplate question. Boilerplate means, you know, it's there every time, it's simple, and you do the same procedure every single time. It's a computer science term, but anyways, okay. Any questions about that? Okay, so now how does this turn into an electric field question? Well, it's simple. Instead of the question giving you the charges and saying what's the net force in a charge, it omits one of the charges and says what's the field strength at that point. You just go ahead and put a charge there. You decide what the charge is, and you divide the charge out after. So let's say the question was exactly this. So they didn't give you a charge at C. They just gave you a point. Then they're like, what's the electric field at C? Well, to do that, there's two ways. You can go hunting on your equation sheet, frantically looking for electric field equations, or you can understand the physics and instead just say, okay, well, I'm just going to put a charge there. Call it C, make it +1 Coulomb, and do the exact same problem. And then the difference is, in the end, when you get this net force on this charge C, which you've totally made up, all you have to do is divide out that 1 coulomb charge. Then what's your unit's gonna be? Your unit's gonna be newtons per coulomb, which of course is the net electric field at that point. So when you're looking for electric field, it's just that little twist at the end. Just divide out the charge, that's all you gotta do. Yeah.
So like, once you find the FC, you just gotta divide out the 1 coulomb, that's it?
Yeah, because that's the charge you place there. Because that's not part of the system, right?
Yeah.
Like you put that there to test the system, so you gotta divide it out when you're done. Like it's just a tool you're using, right? It's like doing surgery and sewing up your scissors inside the patient, right? You gotta take the scissors out of the patient before you sew them back up. Same idea, you're just going there, you're doing something, you gotta take your tools with you when you leave. So take the charge with you. That was a weird analogy. Obviously my analogies are totally unscripted, they just come out of my mouth.